Denevi, and she'll be talking about global variability in regolith properties on Vesta.
All right, thank you. So I wanted to just go through some of the questions that we're kind of looking at answering with this work that include just rather, broad, general questions about regolith on airless bodies, and then some that are more specific to the peculiarities of Vesta. So, for the general, what does the regolith look like on a body that is intermediate in size between these small asteroids, which can essentially just be 100% regolith as a rubble pile, and, planetary-sized bodies, Moon, Mercury. And then, a question you might ask for, other bodies as well is context for samples. In this case, the Howardites, which are regolith breccias thought to originate on Vesta. And then, of course, context for the spectral and compositional information that comes from dawn. For example, can we identify bedrock in any locations? What would the composition of that be? And then, how thick and mobile and well mixed is this regolith? Is it a situation where you're really homogenizing things across the surface, or do strong variations in composition still remain? And then for Vesta in particular, it appears that lunar-style space weathering is really not occurring to a substantial degree. There's not the same changes in band depth and slope that you see. And regolith mixing may be the dominant form of space weathering there. So, how much mixing are you getting, and on what kind of time scales? And then another question that, so far for the handful of asteroids we visited appears to be particular to Vesta, is this question of the origin of the high abundances of hydrogen as measured by the GRAND instruments, and then OH as measured by VIR, which you see in fairly high abundance across these broad equatorial regions mainly. And so that's been suggested to be due to a more ancient regolith in these regions that's been able to preserve the accumulated exogenic debris over time, specifically some of the carbonaceous material that's also observed in the Howardites, and can be seen in pretty substantial abundances. Some of the spectral modeling suggests tens of percent, and was seen at an abundance of 60% in one Howardite. So how does our look at the regolith tie into this picture? So we've been looking at estimating regolith depth, and we're using images from Dawn's low altitude mapping orbit, which had nearly complete coverage south of around 55 degrees in Earth. And that was because during the low altitude mapping orbit, the northern regions were in shadow. It was northern winter. And those images are around 17 to 20 meters per pixel, which is really fantastic coverage. But many of the methods that have been developed for studying the regolith, specifically for the Moon, were from images that were on the scale of 1 meter per pixel. And most require images that are less than 10 meters per pixel, or something like a seismometer. So we're adapting techniques that have been used on other asteroids as well as the Moon, and looking at things like boulder distribution, small crater distribution, observations of crater walls, rather than some of the more classic techniques for the Moon, looking at, for example, the interior crater morphology, as done in studies by Quaid and Oberbeck and Quaid. So I'll go through each of those, and then we're also looking at just models of regolith production, also originally developed for the Moon. So looking at the block distribution, craters with blocky ejecta, in kind of the simple-minded sense, are likely to have penetrated through the unconsolidated, finer-grained regolith to eject more coherent material. So in principle, these can help you pinpoint locations of thin regolith. in actuality, there are some more complications. For example, individual craters can excavate blocks from within the regolith. Cratering can create blocks in regolith breccias. So we're looking at just kind of the broad regional distribution to average out some of this. So we mapped the diameters and distributions of all block-rich craters. Here are a few examples where the arrows are pointing to blocks, if you can see that. And we used the entire LAMO clear filter data set, found 156 craters between 680 meters and 70 kilometers. But these huge craters we're not quite as interested in. We're focusing on those less than 10 kilometers in diameter, which should give you information on the upper 1 kilometer or so of the surface. But of course, since our smallest crater that we can identify with blocks is 680 meters, we're missing some of the smaller ones simply because we can't resolve blocks around those craters, and we can't look at any of the finer, shallower layering with this method. Oh yeah, and I just stuck this in here since I saw everyone's projector woes. So you can actually see, hopefully, some blocks of the sun coming from the east. All right. Oh, and this came out okay. So this is some examples of the distribution of blocky craters on Vesta. And just looking at, focusing on two regions. This is shown on top of a framing camera color. Both of these are stretched the same, and hopefully you can see one of the interesting things about Vesta, this fairly large albedo difference that occurs between, this is the Rhea Silvia Basin here. The South Pole is around here. So I've tilted it up here to show you. And then these kind of broad equatorial regions, which are low in albedo. And you can see these black circles are the craters that have the block-rich ejecta. And we get a high concentration within Rhea Silvia, which may have formed as recently as around 1 billion years ago. And then this broad region of low albedo, really we don't see any craters less than 10 kilometers that have exposed blocky material within here, consistent with an older age, a thicker regolith. And this is now also just shown here on top of a hydrogen map from Tom Prettyman, where the abundances are in this rainbow color from 0 to 400, that should say micrograms per gram. As has been previously shown, the albedo is correlated with the hydrogen abundance, and so we of course see few blocky craters in these hydrogen high regions. I just note a few exceptions that we do see are typically either on the rim of this other large southern basin, Venonea, or some of these are on local topographic highs, areas where you might expect more competent material to be exposed closer to the surface due to downslope material of regolith. We've also been looking at observations of crater walls. And one of the interesting things that we see is this kind of spur and gully type erosional patterns that are observed in some crater walls, where you can see here hopefully some of these resistant spurs. In a few craters, not as many, we do see evidence of just kind of a layering, perhaps a strength discontinuity exposed within the wall. And so these are consistent really with mass wasting of materials downslope, where you'll have material resistant to erosion near the surface. And I'll just note that for asteroids, these features are fairly rare. The only thing that comes close is maybe 3 craters where there was some potential hints of this on Eros. So what are we looking at? These could be due to simple strength discontinuities in the regolith, where you have just kind of a weakly consolidated material or consolidated breccias, so areas where you see craters that have penetrated through to the megaregolith, or possibly bedrock in some cases. But a lot of work has been done, on slope stability experiments for terrestrial applications, landslides, etc. And some of that has been also applied to Mars, where you see some of these resistant spurs. And those have been shown to be analogous mechanically to something like glacial till, possibly. So this is definitely not requiring bedrock. So looking at the distribution of these across Vesta, we also see a similar pattern. There's a good correlation with those that have block-rich ejecta, and fewer of these within our equatorial low albedo region. A lot found within Rheosylvia and other regions. And note again that many are on ridges or other topographic highs. I just wanted to point out one example that's also interesting in terms of the ties that we're finding with composition. This is a Runcha crater in the northern hemisphere, noted by Amanito et al. As having a high olivine concentration. And interesting, since it's in the north, away from the southern hemisphere basin, which is one would have expected potentially to have exposed olivine from the mantle, but it's not found there. But so the olivine was found specifically in some of the in the crater wall as well as the ejecta. And you can see this is one of these craters where you have resistant material exposed near the surface. And here's the crater on a topographic map from Bob Gaskell, where you can see this region, this higher region, this crater abuts here, and potentially exposing in this wall. And interestingly, olivine is also found in this crater here, which also is abutting this higher region of topography. So potentially evidence that this could be, more consolidated material, whether that's ejecta from, an older basin in megaregolith, or potentially in situ material, I think could be supported by this. We're also looking at small crater populations. I won't dwell on this too long, but you can imagine that if you have a crater that's formed in a really loose material, it's not going to be preserved as long, and that's what you see in the highlands. Hopefully you can see, relatively few small craters compared to a Mare region here. And so if you look at the crater size frequency distributions, you can usually see for both the Mare and highlands and then other asteroids that you have a lower density of small craters that have formed in this, unconsolidated material and are eroded more easily, especially on asteroids where seismic shaking is going to have a larger role. So we've been comparing the crater size frequency distributions for some of these same areas, and this is just a standard reverse cumulative histogram where you can see for the equatorial region shown in red. It's not getting out to very large diameters here, but you have more a higher abundance of craters at the large diameters, but at some point these trends cross over and you have fewer at small, and the same thing shown in the R plot. We're also comparing these to other bodies, specifically the moon, the lunar highlands shown down here, and an area of Eros also shown down here, compared to lunar Mare and another region of Eros that is thought to have thinner regolith. So we haven't made too much of this comparison yet. This work is actually, these counts were done by Peter Thomas, published in Robinson et al. 2002. So I wanted to redo those before myself at images of the same resolution before I worry too much about potential differences there. Finally, something that we haven't gotten too far on, but have started looking at Monte Carlo modeling of regolith production. So for a given area, this would be a 1 billion-year-old surface, potentially like the Rheosylvia Basin, looking at just randomly putting these craters down, tracking their ejecta, whether it was pre-existing regolith being excavated again or new regolith being added, and then you can get a distribution of regolith. So far, it seems to give results that are thinner than we would expect from the images and are more homogeneous, but we're still examining that. And then just to put this in context of other asteroids, Itokawa, which could be considered to be all regolith, and then Eros, and Lutetia, where you had really, highly mobile regolith. The distribution, the regolith on Eros was quite thick and was thought potentially to be one of the reasons you don't see a lot of diversity in color properties on Eros, because it's really been homogenized and wiped that, removed traces of compositional and space weathering differences as well. But for Vesta, we do see substantial regional variability. Large regions where craters up to 10 kilometers in diameter do not excavate coherent material. So that could indicate the regolith is greater than 1 kilometer deep in those areas, or also that you just have a thick regolith that's promoting rapid burial of any excavated blocks. And I think that as we develop this more, the model results can help constrain what that actual depth is. So I've talked about the small crater populations and the crater walls really supporting the same result, the thinnest regolith in portions of Rhea Silvia. We've also been looking at the distribution of small-scale grooves and fractures and things that are not as well preserved in thicker regolith. But I think overall we can say that we don't have any areas where we can clearly and definitively say bedrock is exposed, except perhaps in some of these large cliffs and scarps seen on Rhea Silvia. And then we are finding that this is consistent with a suggestion of hydrogen, in the form of carbonaceous exogenic debris accumulating for long periods of time in some regions of the asteroid, whereas anything that was, any regolith that had been there, for example, in the Rhea Silvia basin, was removed by that impact event. And it's clearly not homogeneous to the degree of smaller asteroids. We see a lot more local variations and more evidence for coherent material at depth. Thanks. Any questions?
Brett, I wonder if you could get some leverage on the block and rock abundance that's below your image detection limit by looking at the temperatures derived from the thermal correction of the VIS-IR data and putting that into a rock abundance model, kind of like we've done for the moon. I think there's some clearly understood issues related to the accuracy of those temperature derivations, but it still might give a cool first order number that you could, one, compare to the imagery, but also kind of go beyond that and get, whatever the pixel size, you can, you're sensitive to rocks that are, would be much, much below the detection limit of frequency in the imagery.
I think in a few cases that may be possible, but the resolution of the VIR spectrometer data is really low, hundreds of meters per pixel. For the areas when they had the best coverage at the best illumination angles and things. So I think there would be a lot of challenges doing that, but it might be possible for a couple of the larger examples.
Okay, one more quick one.
I think it'll be quick.
Mm-hmm.
Nice piece of work, Brent. Have you had a chance to look at the regolith loss amount for Vesta, say, compared to the moon? Because it does have lower gravity. What I'm wondering about is the accumulation rate of the regolith, or the retention of the regolith for Vesta, say, compared to the moon.
Yeah, I mean, there has been a lot of work done by others on looking what that rate would be, but I don't think that our the results that we would get would be specific enough to really constrain that very well, because it's hard to define this transition of regolith to megaregolith to bedrock. So I don't think we would put really strong constraints on that, other than clearly they're retaining a lot of regolith, and it's not, as was once potentially postulated, that asteroids would have very thin regolith with very little retention. But.
Okay, great. Thank you.